Hello! Welcome back to Piers Rocks. In a previous episode we investigated this 2031 disk drive and discovered it had 1541 internals. I converted it back into being a 2031 disk drive, but I also found that the original drive mechanism from the drive was faulty. Today I'm going to fix it. I found at least two problems with this drive unit. The first was that the old belt that came on this unit was incredibly loose, and in fact a screw had been put into this hole here and the whole belt had been routed around that screw to add a bit of additional tension. I've since replaced the belt, but I think it may still be a little bit too loose. We'll have to see. Looking up the specs online, the measurement for the original belt was 288, which I assumed was millimeters and circumference. With my rudimentary math skills, I turned that into a diameter, which I got as 91.7, and then bought the nearest size belt I could find on eBay. That was 91 millimeters. As I say, it's still a little bit too loose. We'll have to see if it works. I mean, it does seem to work, but at full speed, I don't know. The second problem I found is much more challenging, and that was that the tachometer for the motor that actually drives this spindle is faulty. So the motor is located over here. If I turn the unit over, this is the motor here, and actually I've removed the tachometer winding from it. Normally you'd see a cap over this bit, and these two wires, the grey and the yellow wires, would be attached to that cap. So that tachometer measures the speed of this motor. That speed gets fed into this circuit board here at these two positions. Again, I've disconnected the wires at the moment from this circuit board. The signal from the tachometer is rectified using 4 of these diodes here and then fed into this IC, which then controls the speed of the motor. So basically it's providing feedback to this circuit so it can spin the motor at the right speed and is aiming for 300 RPM. Because the tachometer had failed, I was getting 450, even 500 RPM out of this unit once it had warmed up. Now, if we think about the theory of how a motor tachometer works, it's essentially a small generator. So I'm assuming this is a magnet on the end of the motor. So when the motor spins, this magnet would also spin. The tachometer is a coil of wire that sits around this magnet. Because there's a magnet spinning inside a coil of electric wire, a current is generated in that wire, and that is the voltage associated with that current is then being read by that IC on the other side of the board. We'll take a look at a working unit and we'll see what sort of signal we're getting out of the tachometer from a working unit. I'm not going to connect this up to a disk drive and get it working because I have verified that this tachometer is indeed broken. I'll show you that in a few minutes. I have a working 1541 dismantled in front of me. This drive mechanism is a working drive mechanism. It's upside down, so I can connect the multimeter up to the grey and the yellow wires coming from the tachometer from the spindle motor of this unit. I've got the fluke hooked up to it. We're expecting to see an AC signal coming out of the tachometer, so I'm going to measure it with the fluke. Obviously it's an AC signal because the tachometer is essentially a mini generator in this circumstance. I've got a formatted disk in the drive so I can run the speed test over on my Commodore 64, which I'll kick off now. So I'm saying 300.0 RPM on this drive, which is the ideal value. Not surprising because I've serviced this drive. And we're seeing a signal of 2.96 volts coming out of the tachometer. In terms of the frequency we're seeing 377 Hertz from this drive unit. Now, it's not terribly easy for me to test the failed drive unit in the same way as a comparison, but I have run the same test and can report the results. I was seeing an AC signal coming out of the tachometer, but it was very, very weak. The amplitude was about 280 millivolts, so less than a tenth of the signal coming out of this working unit. The frequency was about 600-700 RPM, which is not surprising because the IC on that drive unit wasn't getting a signal from the tachometer. It was driving the spindle motor just as fast as it possibly could, and therefore we were seeing a much higher frequency coming out of the tachometer. But with an amplitude of 280 millivolts, that's not even going to overcome the forward voltage of the diodes used to rectify the signal before it goes into the IC, so the IC can't see any signal at all coming in from the tachometer on that failed unit. So here is the tachometer removed from the failed unit. To remove it, you just undo the two small screws that are attached here and lift it off. Now the cables coming from the tachometer are attached to this unit, so you'll flip it over and you'll find this bit of, I don't know, plastic, wax paper, something just to act as an insulator between the tachometer circuit board and the main motor body. You'll need to remove that, and then the two cables coming out of the tachometer are soldered onto these points on the circuit board. You'll need to desolder these points. Now on the other side of the circuit board here are where the winding from the tachometer actually attached to this circuit board, and this circuit board basically just connects the windings through to the cables that then go to the PCB on the underside of the drive mechanism. Now what I found was both winding wires were soldered here, but if we then look a little bit further underneath here, this whole unit is glued in place. I'll talk about removing this in a second, but I've broken the glue on this unit. I found that both windings came out and came through here, and I discovered looking at it closely that one of the windings, while attached to this circuit board here, was then broken inside where the winding starts. So presumably when this is made, there's a loose bit of wire on the inside, then the wire, however many loops, is coiled round, and then you have a free bit at the end, and those are the two ends that are soldered to this circuit board here. I found that the wire on the very inside of the winding had snapped as it came out of the body of the winding. In fact, even under a microscope I couldn't see the wire on the winding that had snapped, so I don't see any particular way to rectify this particular winding, so I'm going to need to rewind this tachometer. Now, talking about the other construction details used here, this, as I said, was glued in to the cap, so there's a ring of glue adhesive round the inside here. So the way I removed this whole unit when it was in was I got an angled dental pick, one of the blunt dental picks, not a sharp one, and I just slowly went around levering it out bit by bit, and it came out within a minute or so. It was fairly straightforward. And then if we look at the other construction details here, if I can get this back out again, there was a plastic post had been sort of squished or melted in the way of removing this metal plate. I snipped those off with some flush side cutters, and that then enabled me to remove this metal unit, which just seems to have a series of fingers around it. There's another on the bottom with fingers that come up. I don't know that these fingers actually perform any particular function as far as the signal of the tachometer is concerned. It may just be there to stop the magnet from hitting and wearing away the plastic body of the winding. That's my theory anyway. To rewind this, I don't think you need to remove these metal fingers, so you don't need to snip these plastic posts. It all fits together quite snugly again, so I don't think I'm going to need to glue that back together. In terms of doing the rewinding, there's some adhesive on the outside of the winding holding the wires in place. I can't actually see where it is at the moment. I could see it under the microscope. I think it is here where the wires came out of the winding. There's just some glue here. So I don't know that I'm going to be able to easily and non-destructively unwind this existing winding. Although I might be able to. Right? I mean that seems a little bit stuck at the moment, but it is coming if I give it a bit of a tug. In any case, what am I going to rewind it with? Well, I measured this magnet wire with my calipers, and I came out with a reading of 0.08 millimeters, so 80 microns, which is about 3/1000 of an inch. And looking at some charts online, that seems to be around about 40 AWG wire, maybe 41, may even be 42. I actually bought reels of both the 40 and 41 AWG wire in hope I could figure out which of the two was being used. Actually, thinking about it further, I don't think it really matters, because I think so long as the IC on the drive mechanism PCB gets a signal of the appropriate frequency, so long as the amplitude is, you know, roughly in the right ballpark, I don't think the amplitude is going to matter very much. And I think the precise gauge of the wire is just going to change the amplitude, the voltage of the signal slightly, because different wires will have a slightly different resistance. The service manual for this drive says that the total resistance of the coil winding at rest should be about 175 ohms. So that's what I'm aiming for, and I'll aim to rewind this so that the new wire is about flush with the edge of the plastic, because that's where it is now. And I'm hoping I'll get in the region of 150 to 200 ohms, and that should be sufficient to get the appropriate signal out of the tachometer. We'll see. Next thing is I'll show you the setup I'm going to use to actually do the rewinding of this coil. Here's the equipment I'm going to use to rewind the tachometer. So I've got I think this is 40 AWG wire here. I've got this sitting on a little holder that I previously made when I was winding some solenoids for pinball machines. Just a bunch of 3D printed parts to hold the spool in place. I'm going to use my drill to turn the tachometer housing itself. And again, another part I made when I was winding pinball machine solenoids is this little tool which has a hex adapter to go in the chuck of a regular drill, and then I will stick the tachometer housing on it like that, and then screw this washer or clamp this washer into the end using a screw through the middle of this tool. That should hold it securely in place, and then with the drill here I can turn the whole winding as many times as I need to fill this up with the 40 gauge wire. I don't know precisely how many turns that's going to be. When I was unwinding the unit, with a highly unscientific measurement of arm widths, I estimated that there was maybe 50 or 60 meters of wire on this housing originally. So let's get to it. Right, I started off the winding in the housing. So this is the initial piece of wire that comes through the gap in the housing. I'm now going to try and attach this to the tool on the drill and then screw it in place, hold it in place with the washer. I've folded over the initial piece of wire. I'm hoping that will get clamped in place by the washer so it doesn't wave around free. So let me try and attach this now. So I need to hold it in place, and I need to get the screw through the washer into the end of the tool, which I have already pre-drilled so the screw will easily tap into place. To tighten this screw up. Okay, that is starting to bite now. That feels really snugly held now. So it should just be a matter of me turning the drill in the right direction and helping the wire come out of the spool. There's two things you have to do when winding a coil like this. One is you have to put some back pressure on the coil in case you stop the drill. This will just keep on going. You'll end up with spools of wire everywhere. The second thing you need to do is you need to just slowly move it backwards and forwards so it fills up the entirety of the housing, so you don't just get one big pile of wire and the rest of the housing free. Now, I'm hesitating slightly because I don't know which way the drill's going to go. I can run it in reverse, but I don't know which way it's going to go, so I'm just going to run it very, very slowly to begin with. So that is the correct direction. So I can now start winding the entire coil. Just pausing to check that no wire has escaped around the edges of the housing. Looking pretty good so far. And I'm maybe about halfway through. Just pausing to put on my finer reading glasses. Alright, I've caught some wire around the edge. Okay, there we go. That is where it should be now. I think I've also caught some wire around this front edge. There we go. That was it, I think. No, is there still some there? Very difficult to tell. Alright, I think I've got it. I think what I'm actually going to do is I'm going to call it there and see whether this works or how it works, what sort of amplitude of signal I get when spinning the motor. I'm just worried if I fill it up any more I'm going to get more going around the edges. Let me just have another look at that. Yeah, I don't think I have it around the edge at the moment actually, so I may just keep on going for a little bit. Nope, did that go around the edge? Yes, it did. Yeah, I'm going to leave it there. See how that goes. It seems quite well attached to the spool, so I don't think it's going to just magically unspool itself when I take it off the tool. But I will get a sticky label ready to stick it all in place once I've got it off the tool. Right, screwdriver. There's no wire that side other than the inside piece. Don't see any wire that side either. So I think that's a pretty good wind. Let me stick that in place there. Can't see what I'm doing. So if I just stick it in place there, I can now disconnect from the reel. I'll leave myself plenty of extra wire. So I think as the next thing I'm going to do, I'm going to place this over the end of the spindle motor from the failed unit and apply some power externally to the spindle motor to make it turn, and see what kind of voltage and frequency, but primarily voltage, I get out of this winding. Before I actually try this out with the real spindle motor, I thought I'll just double check the resistance of the coil that I've wound. So when soldering to this sort of wire, magnet wire, the wire is coated in a very thin layer of insulating enamel. There are two ways of getting rid of the enamel so you can actually solder to the end of the wire. One is you can scrape it off with fine cutters or maybe an X-Acto knife. I've never had a great deal of success with that mechanism, particularly with wire so thin. So the approach I use is I just leave the end of the wire in a blob of solder on the tip of my soldering iron for a while, and once the solder starts sticking to the end of the wire, you know you've burnt a bit of the enamel off, because the solder is actually now sticking to the wire itself. It tends not to want to stick to the enamel. Now, to actually then get this connected to some crock clips, I've soldered some old component legs onto the end of the magnet wire so I can test the resistance. So let's see what resistance the Fluke gives us for this coil. So 190 ohms, that's fairly close to the expected value or desired value of 175 ohms. So I'm reasonably positive that this will work. We may see a slightly lower amplitude signal given the resistance is higher. We may not. My electromagnetic theory isn't very strong. Welcome to my extremely janky test setup. So what you're looking at here is this is the non-working drive mechanism with the tachometer that I've rewound placed around the magnet at the end of the motor. I've disconnected the red and blue wires from the circuit board at the other end and attached them to a bench power supply here. So blue is negative and red is positive. I'm using black for negative to the bench power supply. Then I've got the tachometer, both ends of the tachometer hooked up to my Fluke multimeter. You can see some bits of paper or sticky labels here. I've stuck those to the motor housing to avoid shorting the end of the tachometer windings via the motor housing. It's just gently placed in place. I don't quite know what's going to happen when the motor starts turning. I guess we'll find out together. Before I do start the motor turning, let's just have a quick look at the resistance of the coil. Okay, we're seeing about 160 ohms now. That's lower than we were seeing before. Much closer to the value that I would expect, given I think I've slightly underwound this coil. As a reminder, the value in the service manual for the TAC coil is 175 ohms. I think it's now cooled down since I was soldering on these bits of metal to the end, and that means the resistance has gone down. Anyway, I've got the bench power supply hooked up. I've got it set to 5 volts and 220 milliamps. It needs a slightly higher current to start up, and then it will sit and hopefully run at about 100 milliamps at this voltage. I'm just going to hold the TAC in place because I don't actually know if it's going to try and turn when the motor goes around. Yeah, it is going to try and turn. So if I hold it in place, I think I'm still attached. Just going to turn it back, place it to where it was before, and then I'm actually going to hold the TAC in place so it can't move with my tweezers, and we'll see what voltage we get out of it. No voltage at all, but that's because the motor's not going round, because I'm holding the tack too hard. Let's try again. Now, still not wanting to go round. Let me try like that. There may not be enough power. I'm going to increase the current at this point. I'll put it up to 320 milliamps. See if that starts it. Right, it's running now. We're getting a voltage of 0.8 volts and a frequency of 190 hertz. Yeah, that's pretty good. So obviously this isn't the best of setup, so there's quite a bit of resistance being introduced by how I've got the tachometer sitting right now. It's rubbing against this magnet, but I'm seeing a decent voltage coming out of it. I'm going to try running the motor a little bit faster. I'm going to up the voltage a little bit at this point. I'll set it to 7 volts. Hold the tack gently in place. Okay, 2.2, 2.3 volts. And we'll check the frequency of that. Yeah, 400 hertz. So that says to me that our tachometer might work, because we're seeing a decent voltage coming out of it, that even when rectified, the IC on the control board should still see a signal coming in. So the next thing I need to do is put this tack back together. I was avoiding putting it back together until I checked that I was getting some kind of sensible signal out of it, because I think I'm going to have to glue it back in place so that it doesn't create a lot of resistance for the motor unit. I'll do that now. As you can see, I've got this drive mechanism hooked up to a disk drive. This is a 1541, not the 2031 yet, because I can only easily run a speed test using a 1541 disk drive. I shall turn the disk drive on. Okay, it spins. No idea if that was spinning at the right speed. Turn the C64 on. Spins again. And I shall put a disc in. And do a speed test. So the speed test is saying about 260 RPM. It's getting slightly faster, 263. Now that's not necessarily a bad thing, because I adjusted the speed of this disk drive using this potentiometer here when I first found out that the motor was going far too fast. So I'm now going to try adjusting this potentiometer and see if I can bring this drive back in spec to about 300 RPM. I found an appropriate flat blade screwdriver now. Let's turn the disk drive back on. Now the spindle motor span, but the spindle itself didn't turn that time. I'm guessing because this belt is just a little bit too loose. Let's see if we can get the speed of this disk drive adjusted anyway. So I think now it's going a bit too slow, so it's refusing to run the speed test. So I'm just going to adjust the potentiometer about a quarter of a turn and run it again. We try turning it a bit further. That's all the way at the other extreme. So this is all the way at the other extreme now. I can see it's hit an error. We turn it all the way back in the other direction. So 2 steps forward, 1 step back. I think I really need to try and tighten this belt in some way. So I've put the belt around the screw here. Let's see if that has any impact. 275 RPM. 289 RPM. that is hovering around about the 300, 301 RPM mark. So that's pretty successful as far as the tachometer rewinding goes. I just need to source a better sized drive belt. It's a few days later and I've got 3 new belts. I've got an 88, an 82 and an 85 to try out. These are all 4mm wide. The original belt was 3.2mm by 288 circumference, 91.7 millimeters diameter by my maths. 3.2mm belts seem a bit awkward to get these days. I expect they're 1/8 of an inch. 4mm are much easier to get hold of. I've put the 88mm belt on here instead of the 91 I had previously, and I've adjusted the drive so it should now be running at about 300 RPM. Turn it on, it spins. Run the speed test. .4.7, wavering slightly as you'd expect. So what I'm now going to do is I'm going to actually leave the drive running, performing some operations for a little while, just so it warms up. We get a bit of extra slack, a bit of extra length in the belt due to the heat, and I want to check that it still operates fine after it's done a bunch of work. So the way I'm going to do that is I'm going to run the alignment test on a loop. I think I did run an alignment test on this drive mechanism when I was first testing out the 2031 that it came from, but I seem to remember that the alignment check was giving me some dubious values. I'm much more trusting of the values I'm getting from the tool now, and it seems to be giving me about 1 track out for each track. So track 18 is actually reading track 17 on the disc. This is a disc that I mastered on another of my 1541 drives, and I tend to trust the alignment of my existing drives because I've checked each of them. Anyway, I'm not going to worry about the precise alignment of this drive unit at the moment. I just want to run it over and over and over again just to heat it up, make sure this drive belt is a good fit for the drive, and if it's not, I'll try the 85mm belt. I ran the alignment check for about an hour and I was getting consistent results where it was reading 1 track lower than it should have been reading. So when it was trying to read track 2, it was reading track 1. So I'm going to realign the drive now. Because the drive was reading a track lower than it should have been, it means that the head is actually too far in that direction. This is the stepper motor that controls the head track movement. So that means that this is currently too far that way, too far counterclockwise. So I need to turn it slightly clockwise. So there's a screw here and a screw here. Can't tell if they've been moved previously. I'll probably be able to tell when I unscrew them. So I'll unscrew them, loosen them, and then I will start running the alignment check, and I will live turn this just slightly clockwise and see if I can get both a good reading from the track perspective, but also I'm looking to get a fairly good reading on the half track perspective. So the right hand column of figures that will appear with the alignment check show the half track alignment, and you won't get that perfect for every single track, but I'm looking for that value to be sort of plus or minus 0, as in some of them less than 0, some of them more than 0, and all of the regular tracks being in the right place and reading 100% of those. Those screws work quite tight, so it's possible this has not been aligned in the past. So now I'll run the alignment utility. Yeah, so I'm 1 track out. May need to loosen the screws some more. Yeah, so the reason I couldn't turn the stepper motor is because it's already turned clockwise as far as it will go. So there are little holes in the bracket holding the stepper motor on, which allows a certain amount of travel to this motor unit. So if I turn it fully counterclockwise, I'm a long way out, at least 2 tracks out. If I turn it fully clockwise, I'm still a track out. So I'm going to have to finagle something here so that I can actually turn this, either turn this stepper motor more, or actually somehow move the head mechanism carrier where it's attached to the drive belt, that then in turn connects to this stepper motor. So I'll have a look at this and come back to you. So I did take the stepper motor unit off and increase the size of the holes in the bracket so I could rotate the alignment of the stepper motor more to align the system. But actually I realised I didn't need to do that. That wasn't the right way to approach the problem. Turning the stepper motor is only to take out minor alignment errors. My problem was that the track 0 stop was in the wrong place. So right now the heads are at track 18. I'm going to take them back to track 0 and watch this wheel. It will rotate clockwise that direction, and this high bit will bounce against this track 0 stop. So now it's at track 0. If that is in the wrong place, then all of your alignment is going to be off. Mine was in the wrong place by the order of a couple of tracks. I've now readjusted this so it's in roughly the right place, and then done the fine adjustment with the stepper motor. But there's another problem. Those of you who are more familiar with Commodore disk drives than me will probably already have spotted it. This is not the proper track 0 stop. In fact, this looks like a bent paperclip. In a proper disk drive, there's actually a significant piece of metal here, not this bent paperclip approach. I'm worried every time this wheel bounces against the track 0 stop, it's actually bending it and deforming it slightly, and the whole unit is going out of alignment. I've aligned this so many times, then I do some head bumping and it goes out of alignment. So what I want to do now is I just want to see what the alignment's looking like. So you may not be able to see this very well, but it's showing me that it tried to read track 1, it read track 1, it read 100% of track 1, so that's all good. Then this final column is showing me between each track, so this head can be moved half a track at a time. It's trying to read a half track, and it's showing me whether it can read the track before or after the track it was trying to read. These are all negative values, so I assume it can read some of the track before the half track rather than after. I think the best result is 0. It can't read anything, then it's precisely in the middle, although that's very rare. You won't get 0 for all of your tracks of even a really well aligned drive. But right now all of my values are slightly negative, so I'm just going to allow this to run to completion and look at the values. Alright, all of the full track values were 100%, great. One of the half track values was minus 100, so I'm going to say that's good enough. I'm going to need to try and figure out a better track 0 stop, because as I say, I think this will deform over repeated head bangings, and therefore it will eventually go out of alignment. But seeing as I have the drive well aligned at the moment, I'm going to try a final test with the 1541 that this is currently attached to before I reinstall it in my 2031. That final test is to load a copy protected version of Arkanoid 2. So here I have a copy protected version of Arkanoid 2. This should take about 40 seconds to load. In a few seconds this screen should go black and the game has fully loaded then. Yeah, there we go. loaded perfectly. So I'm going to declare this drive mechanism fixed. Really pleased to have successfully rewound the tachometer coil. A bit frustrated to find this track 0 problem with this drive. I think it must have had a pretty hard life. Anyway, now I'm going to put this back into the 2031 that it originally came in. I have the 2031 back together with the repaired drive mechanism installed. First thing that I'll do is do a directory listing of the 2031 demo disk that I previously wrote on a different drive or drive mechanism. So yeah, that worked fine. We'll now load the performance test program. And we will insert a scratch disk and run the performance test. As you can see, that performance test passed, so I'm declaring this 2031 fully fixed and fully converted back to being a 2031. Well, there we go. A fully repaired and working 2031 disk drive restored to its IEEE 488 roots. I'm really pleased to have repaired the drive mechanism that originally came with this unit. I wasn't entirely sure that I was capable of successfully rewiring that tachometer coil, and then when I hit those alignment issues, which turned out to be the track 0 stop at fault, I wasn't entirely sure whether I was going to get that fixed as well. If you enjoyed this video, I hope you'll consider subscribing to the channel. Until next time, rock on.